So welcome to the session on folding schemes. We have two interesting talks as part of the session. So let's welcome the first speaker. It's going to be about lattice-based folding scheme from unstructured lattices, and Tu will tell us more about it.
Okay. I check. You hear me well? Okay. So hi everybody. I'm Tu. I'm from Paris, and this is John work with Giacomo Christian from EPFL, and I'm from King's College. And the title is LOVA, lattice-based folding scheme from unstructured lattices. So what is folding scheme and why do we care? So basically, the main motivation behind folding scheme is that it's the main building block for IBC into incremental verifiable computation. So suppose that you have a chain of computation with a function f, so you apply the same function f to your input multiple term, let's say t term, and you want a short proof for this. And what I mean by short is like a proof that doesn't depend on t. So you just need one proof for t step. And this is a very powerful scheme that have a lot of application. So like verifiable delay functions and other application in blockchain. And the main intuition behind constructing this proof is that suppose you have a first proof for the first t-1 step, and you have another proof for the step from t-1 to t, and you kind of want to combine them all together in just one proof, such that just checking this proof is enough for the two. And the important thing is that the proof of the output proof shouldn't be bigger, because otherwise it will depend on t. And that's what we do with folding scheme. And it's a very primitive that's very similar to proof, to general proof, general knowledge proof. And so it have prover and verifier, and they both have access to two instances, and the prover have two witnesses, and they interact with each other. But unlike proof that the prover try to convince, in this way, prover and verifier put a new instant and witness pair, and so we have completeness, and the community say that if they start with two instant witness pair in the relation R, then the output will be in the same relation R. And I want to stress that it's the same relation, so the size doesn't increase, and that's very important. And for knowledge channel, it's the same that if the output is in the relation, then the prover must know the witness with high probability. And the way to prove this is just that with the same in proof. So we build an extractor that can require prover many times to extract the witness. And yeah, another property is that we should have 16. So the proof size should be much smaller than the witness size. Okay, so this is introduced. The folding scheme is actually introduced in Nova, and they build the first folding scheme for committed relaxed I1CS. So another variance of I1CS under the discrete lot assumption. And the construction is very simple. It's actually just you just need a compressing additively homomorphic commitment, and in the work they use Peterson, and they have a generic way to obtain IVC from the folding scheme. So, I mean, for lattice construction, we always have like if we just look at the anti-commitment, then we already have this, right? So what is the problem? I will just tell you in a bit. So in this work, we construct LOVA. So just let's explain Nova, and it's the it's the first lattice based folding scheme. It's based on just Caesar assumption, so unstructured, and more important, not more important, but yeah, to the end we will construct for the construction we will use exact Euclidean norm. Okay, so we start with the anti-commitment for general knowledge proof. And we'll work over the ring of integer GQ. And in this setting, if you want to commit to a subvector S, you just compute a Y matrix A, a random matrix A times S, and you got a commitment T. And yeah, this is just this problem, right? If you have two opening for the same commitment and you just subtract them, and it's a C solution. So first attempt for Lova. So we will work with this relation, the anti-commitment relation. The prover have they have two witnesses and two commitment. It works like this. Okay, and the verify start with sampling a challenge C in GQ. Sent back to the prover. The prover compute a collinear combination. So this is just like a between notation, but it will be reducible. So like this is like a matrix 2 column, and it's just a vector of 2 elements. And this is just like S1 plus C2, sorry, S1 plus C times S2. And then the verify do the same thing, do the same linear combination. So because they did the same linear combination, the completeness should be trivial. So because they correspond to each other. But you can see immediately that the problem is when we do the linear combination for the witness, right? Because the witness size will increase. In particular, it will become beta times some constant. And this way you cannot follow a lot. So this is a problem. But actually, it's a little bit worse than that. Because if now we look at knowledge soundness, so suppose we have the visual soundness, so we have C1 and C2. We have two witness, we extract two witness correspond to C1 and C2. And what you do normally in the lattice by folding lattice way proof is that you just subtract them and divide by C1 and C2, right? And I will call this S2 bar and S1 bar. And yeah, so because it's not really meaningful to divide it by them in GQ, so I just suppose for now that the challenge is just 0 and 1. Even so, like if you look at this, SI bar will increase by factor of 2 because you minus, you check, you minus them, subtract them. So we have three problems. First, when we fold, we will do the linear combination, the norm growth. Second one is, for this is that the challenge size is too small. And then we also, when extract, we also have another factor. And the first is the easiest problem. We use technique called decompose and folding. So essentially what we do is that instead of commit driveway, we will decompose the witness. So we just decompose them continuous-wise by base B. And just for the ease of notation, I could just write it as a matrix, times a vector G. You can think of it as a compact gadget. So B is just the vector of B to the I. Then the verify now is, and then the prover commit to the witness. And then the verify now send a challenge, sample challenge, but the challenge now is not an element anymore, it's a vector because we have many more witnesses. And then the verify send back the challenge to the prover. The prover do the linear combination again. And the verifier now first have to check whether this new commitment is corresponding to the initial commitment or not. And finally, they have put the same linear combination. Okay. So the intuition behind this is that because we decompose it, this SI, the column vector of S delta is very small, and you just stack a subset of them and S together, right? So it doesn't increase a lot if we choose the right parameters. Yeah, but still we still have, so the first problem is done. The second problem is still there because standard error is it's something like 2 to the minus 2k, and k here is the y of the S delta, and that is logarithmic, so that's not good. And we still have the third problem. And to solve the second problem is actually a typical idea is that we do parallel repetition, but this we have to do a little bit different from knowledge proof. from normal proof is that instead of starting with just one witness, we starting with three of them. So now we start with a witness metric and a witness commitment. So this is just a type commitment for matrices. And then they did the same thing. So the prover decompose them and then send the commitment, the verifier now sample challenge. But now because we have much more of them, the challenge now become matrix. And then the provers compute the linear combination. The verifier check whether the commitment is corresponding to the initial commitment, and then do the linear combination. And with that, you can see that it's just the same picture with the default. You just do linear combination, and the soundness now is good according to coordinate-wise spatial soundness, so it's spatial type spatial soundness. But still the third problem is kind of annoying. We still haven't solved it for now. And we some kind of need, this is like an apparent, an inherent problem, and we kind of need an exact number for this. So the main idea behind this is that, so if we take the witness S and suppose that that inner product of S with itself is beta square, and that the norm of S is much smaller than it feels, so that the inner product doesn't include the modulo, then we should have the norm S is smaller than beta. So in a way, it's just that we can express the norm using inner product. So this is just the problem. Instead of proving exact norm, we're just proving inner product in a way. So we now switch to a new relation. In this relation, we add another instant. In the instant, we add another element. So it's a metric D, and D is just S transpose S. And if you look at the diagonal of D, right, it's just the norm of SI with itself. So we just require them to be smaller than beta square. Yeah, and the second idea is that if we write S1 transpose term S is D1 and S2 transpose term S2 is D2, and we look at S star is just the decompose of S1 concatenated with S2. Then this is kind of the witness before doing the linear combination. So if we look at S star times S star G, the inner product of S star G itself, then you see that D1 and D2 appear in the first and the fourth quarter of the matrix, and you have other cross terms. And the idea to prove the norm is just to send S star transpose term S star. So we did everything the same as before. We send D delta, it's just S delta S star before, and then we send the cross term, and then the verifier check whether this norm is corresponding to the corresponding to the initial D D1 D2 or not, and then finally is output the new D prime is just the new instance. So the main idea behind why this is a non-proof is that you look at D delta. So D delta is just you know, if you look at it, D delta is fixed already, and C is sampling from the verifier, right? So this is kind of a many quadratic polynomial, and that's why we use for knowledge soundness. And to the end, proving knowledge soundness is just proving that the random evaluation of some quadratic polynomial. And yeah, but because we are quadratic, so just if the challenge is just J1 one, this is not enough. And then, so instead we take this set -1, 0, 1, so just adding more, but it's more than 2, I guess. It's have more than 2 elements. And then if we fix, yeah, it's just, I just want to say that if we fix some C in the set, then with some probability that we already have another, with some constant or probability that we will have another C prime, just different from C by just one. This is important because remember in the first text we want to divide when we extract, we want to divide by minus of two challenges, and this is just for this. And then using this, because we want to prove a random evaluation of a quadratic polynomial, we use some Shaw's-Lippold argument, and then we can prove that the norm of them are the same. That's the main idea behind that. Yeah, and we implement it with some benchmark, and the group size 40 is megabyte, which is not really good. Yeah, but I mean it's not the end of the world in the lattice literature. And then the prover and the revised time is also quite bad. Yeah. So to summary, so we solved three technical problems to construct a first folding scheme of balanced lattice. So we use decomposed fold for the norm growth. We use parallelization by starting with many instances for the fairness, and then we prove the exact norm by some probability check using inner product.
Thank you.
Sorry.
Questions?
Great talk. Would you please go back to the page where you are showing the benchmark numbers? Yeah.
This one?
No, the next one, I think.
Oh.
No, the next benchmark numbers, the prover time.
Oh, okay.
26, I guess. Yeah. Do you remember that what was the memory requirement in the runtime? Because I see you are testing it on 120 GB EC2 instance.
Sorry, can you repeat?
Do you remember what was the memory requirement during the runtime while doing the proving?
No, we don't have any figure, but I think it should be similar to the proof size because, yeah, we don't do any extra memory for this. So I think it's just the proof size is the same.
You think the proof size will
Yeah,
be
the
the memory
prover memory should be similar to the proof size.
Okay. All right, I'll take a look. Thank you.
Thank you for the great talk. I have two questions. So my first question is that, do I understand correctly that due to the fact that we are using this -1, 0, and 1 as the challenges, it means that we get something like heuristic security because of that?
Sorry?
So does the fact that we use the challenges -1, 0, and 1 implies some kind of heuristic security?
Security for the coordinate?
Yeah, like, I mean, for in the extraction direction.
I don't understand, sorry. For what selection?
So in the extraction direction for the
Oh,
it like
for
as you
the
said that,
extractor.
yeah, it means that it's somehow
Yeah,
heuristically secure.
That's a good question actually. So because I told you right, for the tech two we use restricted. Sorry, we use gradient-wise spatial soundness. But for this one is we have to use a little. We have to have a more specialized strategy to just extract them just by a difference of one. And yeah, that's a technical detail, but we can do it. And the strategy is just the same. It's just the same. Just we have to fix just change some detail in the proof of the of the special soundness extractor strategy.
Okay, so this is not like a generic special soundness extractor. It is some tweaked variant. And the other
Yeah, I
thing,
mean, you can generalize it. Actually, we tried to generalize it, but we couldn't prove it in the general form.
okay, thank you.
Any more questions? So I had a quick question. Do you also have analysis of how to add zero knowledge? So for instance, would techniques similar to hypernova work for you if you want to add zero knowledge?
Oh, yeah. So that's another good question. So for general knowledge, so for IVC, there's the compiler from folding scheme to IVC. There's this generic compiler that you can add general knowledge to it. Yeah. Otherwise, yeah, it's not easy. It's not very trivial to add general knowledge to this book, but yeah.
Okay, thank you. Let's thank the speaker again. Welcome the next speaker for the session. Great. So the second wonderful talk of this session is on fly folding lookup instances, and Albert is going to tell us more about it.
Thanks for the introduction. It's a pleasure to be here and talk about our work on folding lookup instances. So let me recap what's folding, even though it has been recapped already, just to fix some notation. So we fix a relation R, which has pairs X and W, instances and witnesses. And then a folding scheme is an interactive protocol between a prover and a verifier, where both prover and verifier have two instances, and the prover also have valid witnesses if the prover is honest for the instances. And then in this scheme, the prover and the verifier interact to create a new instance witness pair with the following key property, which is that if the new instance witness pair is in the relation, then it is possible to extract witnesses for the original two instances, except with negligible probability. All right, so the TLDR folding reduces the task of proving two instance witness pairs to just proving one. And yeah, in most folding schemes, commitments have a crucial role, and actually we use relations where the instances contain a commitment to the witnesses. So really in folding schemes, the instance witness pairs look like this. There's xi, the instance is the actual public instance, and then a commitment to the witness. So the scheme above really looks like this. There's always the commitment to the instance. And this commitment is most of the time homomorphic, which means that the commitment of the sum of the vectors is the sum of the commitments of the vector. Okay, and how does folding work? If we see it from very far away, so the following is a very simplified blueprint, it's not entirely correct, but it contains everything we need for this talk. So in folding, as I said, we have two instance witness pairs, so let's pick two of them. And then there's a prover and a verifier. Prover knows the two, knows the instance and the witnesses, verifier knows the instances. Then they exchange some messages, and eventually the verifier sends a challenge, a field element usually. And then prover and verifier output the new instance witness. And the key property in most folding schemes is the following, and it is that the new instance is a linear combination of the original two instances using the challenge for the coefficient. And the new witness is a linear combination of the original two witnesses. And the verifier computes the commitment to the new witness using the homomorphicity of the commitment. Okay, and as I said, this is a very simplified blueprint. In reality, it's a bit more complicated. Sometimes there's like error terms that are introduced, and the error terms are a polynomial, an algebraic expression on the error terms of the original witnesses or the original error term. But let's ignore this for now. Okay, so folding schemes have become very popular since Nova. Nova is a folding scheme for the so-called relaxed R1CS relation, which is basically an R1CS with an extra error term and a constant that multiplies this term. And yeah, and after Nova, there's been lots of folding schemes designed for different relations. For example, Hypernova is a folding scheme for the CCS relation, which is a generalization of R1CS. Protostar is a folding scheme for relations that admit a special sound interactive proof. So it is a folding scheme for a wide, very large class of relations. Protogalaxy is a generalization of Protostar. And Neutron Nova is a very recent folding scheme for the zero check relation, which is a relation where a polynomial vanishes on a whole hypersphere. Okay, and you can also design folding schemes for lookup relations. And this is what interests us today. And what is a lookup relation? So a lookup relation for a set S consists of, it has this, is a relation that contains these pairs. So the witness part is a vector. The instance is just a commitment to the vector. And the vector satisfies this property, which is that each entry in the vector is in the set S. Okay, so lookup relation R for a set S is that vector whose elements are contained in S. And a lookup argument is a special proof system, is a special type of NAR for this type of relation. For example, suppose that S is the range of integers from 0 to 2 to the 128. Then a lookup argument is a special NAR that proves that all entries in a vector are in the range 0 to the 128. So it's a lookup argument for this relation is what we call a proof system for a range set. You could also have, for example, S have this form. This is the set of string where the first chunk of the string is a big string. The second chunk of the string is the height, SHA-256 height of the bit string. And then a lookup argument for this set is basically a snark that proves correct computation of SHA-256 on a vector. And why do we need lookup arguments? As I said, they are just a type of snark. So you could just take a standard snark, all-purpose snark, and use it for proving membership to this set, right? But the issue is that arithmetizing set membership to some of these sets is very expensive. So writing membership to S, to this SHA-256 set, using just R1CS constraints or R constraints and so on is very expensive. It can take about 1 million constraints. So we don't really want to arithmetize membership to some of these sets just with a arithmetic circuit over a field. Okay, so what we want to do here is we are concerned about folding lookup instances. And we design a scheme for doing that. So let's fix a relation for a set, a lookup relation for a set S. So remember that RS looks like this. It's just the set of vectors whose entries are contained in S plus their commitments. And now to simplify the exposition, I'll just forget about the commitments and write the statement that this instant witness pair is in the lookup relation, simply as the vector is contained in S. This will simplify a lot the exposition. Okay, so we have two lookup instances. V1 is contained in S, V2 is contained in S, and we want to create a new instance. V3 is contained in S. So that is V3 is indeed contained in S, then except with negligible probability, V1 and V2 are contained in S. This is, again, a simplified picture. We will not just get V3 contained in S for the instance. There will be some extra things. As usual, this is the usual case in folding schemes. You usually have to relax the relation to start with, but let's ignore this. Okay, so what do? We start by recalling. So this is a standard observation now that V is contained in S, even only if there is a matrix M of appropriate sizes, such that all its rows are elementary vectors, meaning that each row is all zeros except for an entry which is 1. And M times the set ordered as a vector is equal to V. Let's see an example to convince ourselves that this is the case and why. So let's say that S is a set of integers 1, 2, 3, 4, and V is the vector 4, 2. Then it is clear that this matrix exists. It's this one. You multiply 0, 0, 0, 1 by the set, by this vector, you'll get 4 and so on, right? So basically what's going on here is that you take a matrix M whose ith row is the position, indicates the position of S, like, equals the I. And it is clear that if M has only, each row is all zeros and has just one entry which is 1, then M times S is contained in S. So if M times S is V, then V is necessarily contained in S. Okay, so with this, and I use RLM to denote matrices of appropriate sizes, all whose rows are elementary vectors. So with this observation, we can replace the claim that V is contained in S by the claim that there exists a matrix in RLM such that M times S is V. And now, if we want to fold these two claims, we can replace V1 contained in S and V2 contained in S by claims of this form. So we get, instead of folding this, we fold these two claims. Okay, and notice that these are linear relations. If we fix S, the table S, which is fixed, parameterizes the relation, then these are just linear constraints. So first thing that comes to mind is just take a random linear combination of the witnesses we have in here, and you'll get new witnesses that satisfy the linear constraint, right? So following the blueprint for folding schemes that I explained before, we could have V send a random element alpha and reduce this claim to this claim in here. So random linear combination of the matrices times S is equal to random linear combination of the initial vectors. And yeah, so we can see that with high probability, 1 is equivalent over the choice of alpha. So now we have this claim, but this is not really good. This is barely any better than the original claim because we still have these two claims in here. M1 is in RLM and M2 is in RLM. So in the next step, we are going to fold these two claims. And the idea here is to define RLM algebraically in the following way. So remember that RLM is a set of matrices, all whose rows are elementary vectors. So we define RLM in a natural way as follows. So we observe that a matrix M belongs to RLM if and only if it is a binary matrix, which means that all its entries are 0s or 1s. And this is in algebraic terms just the statement that the square of each entry is equal to itself. And if M is binary, then M is in RLM if and only if M times the vector full of 1s is equal to the vector full of 1. Because if M is binary, then multiplying M by 1 just adds up all the entries in each row. So M times 1 is the number of 1s in each row. So if M times 1 is 1, then the number of 1s in each row is 1, assuming the characteristic of the field is large enough. So we've characterized membership in RLM as these algebraic constraints. And this is actually the next observation is that these constraints are roughly an R1CS constraint, where the witness vector is the matrix. And this being an R1CS constraint can be folded using Nova type technique. And that's what we do. We fold M1 in RLM, M2 in RLM using a Nova type approach. And the final folded instance has more or less this form. So we have the random linear combination of the matrices times S equals the random linear combination of the vectors, and M1 plus alpha M2 is in some kind of relaxed version of the relation RLM, which appears when you do Nova folding. Okay, and then we notice that these MIs are very sparse. They just have one non-zero entry per row. And using this sparseness, we managed to have the cost of this folding procedure be very similar to the cost of doing a Nova folding on a witness of size, the size of the original vector. And this provides, to our knowledge, the cheapest folding scheme. So the folding scheme for lookup relations with the cheapest program verifier that we know of. However, there's a caveat because we reduce the initial two planes to this plane here. And we use sparseness of M1 and M2 to have this reduction be very cheap, be basically a Nova folding for vectors V, for vectors of size V. But notice that now the folded matrix is losing sparsity, right? Initially, M1 and M2 have, each row has one non-zero entry, and now maybe each row has two non-zero entries after we take this linear combination. If you keep folding and folding, you could end up with a folded statement of the following form. So we have a folded matrix times S is equals a folded vector, and a folded matrix is in RLM relaxed version of RLM. But this M fold might be a full dense matrix of size, the size of V times the size of S. So if you want to prove the folded statement, this could be very expensive. Especially, this could be very expensive if S or V is very large, right? We get a quadratic cost. So we either envision Fly being used for tables that are small or these that are small, or we design a variation of Fly where we leverage the concept of SOS decomposability from the Lasso paper to reduce this factor S to the size of S to 1 over C in exchange for having C small fold, for doing C small fold at each folding step. So by increasing C, we can reduce this factor in the quadratic. So in this quadratic cost, we can reduce the cost of this crossing here to as small as one wishes by increasing by splitting each folding step into small folds. It's not exactly that. It's not C small folds. It's less than that, but that's the intuition of what's going on. Okay, and let me just explain what's SOS decomposability. So this is a concept that has been used, as far as we know, before the Lasso paper, but it was formalized in the Lasso paper. And in there, the authors call a set of elements or table SOS decomposable if its elements can be written as algebraic expressions involving smaller sets. And this sounds a bit vague, so let's see an example. Say that S is the range of integers from 0 to 2 to the 128. This is a huge table. It cannot even be stored in memory, but we can note the following. So an element X belongs to S if and only if there are X1, X2, X3, X4, such that this equation in here holds, the star equation. And each Xi is in S prime, where S prime is the range from 0 to 2 to the 32. So instead of proving X belongs in S, you could prove this equation in here, which is very easy to prove, a linear equation, and then prove that each Xi is in S prime. And this is great because this equation is very simple, and at the same time, S prime is dramatically smaller. And you can see that we could make S prime as small as we want by instead of using 2 to the 32 here, using 2 to the 8. And yeah, so this is an example of an SOS decomposable set. And in a follow-up work to Lasso, the authors show that many sets of interest are SOS decomposable, for example, string 5 instruction. And I have 2 minutes, so I have some auxiliary slides. Okay, I'll use this slide. So how do we leverage SOS decomposability in Flink? Let's take as an example the set of integers from 0 to 2 to the 32. And we use the same trick as before, but now I'm using a smaller expression just to have smaller formulas. So an element x belongs to S if and only if x is equal to x1 plus 2 to the 16 x2, and x1 and x2 belong to this smaller root. So say we want to prove that these contained in the set S, or equivalently that there exists a matrix in RLM, so a matrix all whose rows are elementary vectors, such that n times S is V. Then, following this expression in here, we can write V contained in S, V as the sum of 2 vectors, V1 and V2, time with this coefficient, and then prove that each V1 and V2 are in S prime. So we turn this claim in here, V contained in S, to the claim of V is the sum of these 2 vectors with this coefficient, and Vi is contained in S prime. And recall that Vi contained in S prime, using the trick with the RLM matrices, is equivalent to a claim of this form. Okay, so we end up with, and we can turn these 2 conditions into this conditioning here, where so we replace V1 by M1 times S prime and V2 by M2 times S2, and we get this expression in here. So to prove that this contained in S, we can instead prove this expression in here, and that M1 and M2 are in RLM. So this expression in here can be reduced to 2 linear constraints by using hypernova style sum set. And then we fold M1 and M2 using the Nova style technique I mentioned, and then we perform folding. So we fold the linear constraints that we obtain after the hypernova style sum set, and we fold M1 and M2 using the Nova probe. And now I'll go back to the thank you slide.
Thank you. Questions?
Thanks for the nice talk. Initially, you have taken the example of SHA-1, right?
SHA-256.
SHA-256. Now, how does the lookup table compare to the circuit size of the SHA compares?
So that table is a huge table, and it is not SOS decomposable. So there's no, you cannot split it into an algebra. You cannot express it as an algebraic equation of smaller sets. So currently, there's really not any folding scheme that can any lookup relation that can handle that table. So you would never fold a lookup relation for that table either, because you cannot prove it. You cannot prove the folded instance because the table is too large and it's not SOS decomposable.
How does in general, for any general circuits, how does the lookup table size compare here in this FLI?
How does it compare to?
That lookup table size to any general circuit?
So FLI doesn't have a specific lookup table size. It can deal with, it's a folding scheme for lookup relations of tables of any size. But if the table is too large, it will not be practical.
Okay, thanks.
Any more questions? Okay, I had a quick one. So how does your work compare to using techniques from, some of the prior works, let's say Protostar or something, right?
Yes, so Protostar has a more expensive prover and verifier for the folding part, but then when you want to prove the folded instance, there's no scheme described for doing that, but that should be cheaper than in slide because there's not that quadratic cost.
Thank you. Any more questions? Okay, if not, let's thank the speaker again. Thank you. And thank both speakers of the session. Yeah, let's break for lunch.